Hi there, we're from Game University and IMAC. Today I'm gonna share one of our research. The topic is spatial temporal consistency for semi-supervised learning using 3D radar cubes. Here's the outline. I will briefly introduce the problem that we want to solve and review the related works and talk about our proposed method. And then I will show the experiment results and the conclusions. Recently, radar has become one of the most important sensors in perception modules in many application fields like driving assistance or surveillance system because of its lower price and its robustness against different weather or light conditions. However, the annotation of radar data requires expert knowledge and it is much more time-consuming than general image labeling. And also, the lack of annotated radar dataset has become as a bottleneck in previous research. In order to solve the problem of dependency on annotations, there are many solutions. Some of them use weakly supervised learning to tackle this issue. They usually introduce the external resources to supervise the training of the radar model. For example, LiDAR is one of the most popular candidates. But accessing external sensors has several concerns. One of them is failure modes of the sensors, such as extreme weather or light condition, which might make the external sensor recordings become unavailable. The other one is the ambiguous label when one of the sensors have occlusion. So the label from external sensors might not have a very good quality, which will affect the final performance of the radar detection. On the other hand, there's another group of people trying to use the unlabeled data to solve this problem, different from the radar solutions. Image-based, semi-supervised, and unsupervised methods use the existing annotations and unlabeled data to achieve high performance. They can be separated into two different approaches. One of them is the self-training, and the other one is called the consistency regularization. They try to minimize the difference between the two different input x and x prime. According to different dataset, the x prime could be generated by different perturbations like flipping or rotation or adding noise to the input x. Depends on the dataset, the perturbation could be very different. However, these existing image-based methods are hard to directly apply to radar dataset because of the different geometrical and physical properties. So in the next two sections, I will go through our proposed method and the experiments. I will introduce the two main ideas of our work and then review the whole network architecture. In the experiment part, we will focus on two different evaluation problems and two public datasets. The first part of our proposed method is about the temporal consistency. Here, we use pedestrian detection problem as example. In our previous paper, we simply stack the radar frames in one direction on the timeline to fit into the network. As you can see in the figure, we use 5 consecutive radar frames as the input tensor, use the ground truth to calculate the loss. Then, in this work, we have a new idea that if the goal is to explore the relationship between the radar frames to improve the detection performance, what about stacking the radar frames bidirectional? The reason is that people moving forward and backward behavior should be similar in the radar frames in a very short time period because actually we don't really care about the visual appearance or the pose of the people in the radar data because it is invisible. You can only see the signal reflection instead of the visual appearance. The possible feature might be their velocity and the size of the signal reflection. So moving forward or backward should be very similar in the short-term period. So one of our proposed semi-supervised laws, I call them the temporal consistency, is using the two different directions inputs to calculate the similarity. We would like to learn the relationship between the time step from different timeline directions during the training stage. We stack two input tensor data by using reverse directions. One of them are from t plus 4 to t, and the other one are from t-4 to t. And then we feed them into the same network and use JS divergence to measure the difference between the two output results. These two outputs should be close because moving forward and backward should share the similar behavior. But apparently, this kind of feature cannot apply on LiDAR or a camera because the pose or visual appearance is one of their important features. We cannot ignore them when stacking the data backward. The other laws, the spatial consistency, is much more straightforward. The main idea is that the network should learn the spatial symmetric relationship of the same input data. The difference between this method and the traditional data augmentation is that we only use the unlabeled data to calculate the loss. So the network doesn't know the ground truth. It will only focus on the symmetric relationship between the inputs. So we have two different loss terms. The first one is the supervised cross entropy loss L label calculated by the input Rn. The second one is the unsupervised spatial-temporal consistency loss LST, which could be written as the equation 1 and 2. The D function represents JS divergence and the FL function is the network. So considering both the supervised loss L label and the spatial-temporal consistency loss LST, the total loss would become as the equation 3. The beta function is a typical semi-supervised learning weighting function, which increases the weight gradually according to the training iteration number and gradually decrease the weight to 0 before the training process stops. However, during the training, we found that the overfitting problem is quite severe due to the data imbalance. The data imbalance problem is very common in most of the classification tasks. In our case, the number of the background class is much more than the other targets. During the training, if we calculate the average loss of the whole image, the background class would dominate the loss because there are too many. Only a few points are from other targets. Most of the rest are belong to background class. The model would ignore the other targets. It will predict every output as background to get higher performance. So, in order to solve this problem, we propose a self-weighting mechanism to prevent the overfitting problem. We try to adaptively reallocate the weightings between each class during every iteration to make sure that the model would not only focus on the background class. Here is a very simple example. At the first beginning, we use the labeled input tensor to get the network output occupancy map. And then we calculate the supervised loss L label to get the table 1, which records the average classification loss of each class. The class with higher loss usually means that the model has bad performance on that class. So when we calculate the JS divergence between the two unlabeled input tensor, R hat and R tilde, we can use the table 1 to build a self-weighting mask. According to the predicted class of each location, the class with higher supervised loss will have higher weighting, and the class with lower loss will be ignored. This page is our network architecture during the inference stage. We use the pedestrian detection task as example. In this figure, the solid arrow represents the data flow. We stack the readout queues from t-n to t as the network input, and we define the network output occupancy map as YBAR-T, which contains the predicted class and the location information. And then we use the non-maxima suppression to find the peak of the YBAR-T as the final detection output. Please note that we only stack the input tensor Rn from the previous radar frames. We do not use the future frames during the inference, so our model would not have output delay problem. We only use the future frames when we train the model. I will explain that in the next slide. In this figure, the solid arrow also represents the data flow. During the training stage, there are two branches. The bottom branch, we use the label input tensor Rn to calculate the supervised cross entropy loss L label. The top branch, we feed the unlabeled input tensor pair R hat and R tilde into the network and calculate the JS divergence. Also, we use the L label to build the self-weighted mask WS to reallocate the weightings in every iteration. Okay, in this part, I'm gonna introduce you the experiments we have conducted. We used the two public data sets on two kinds of tasks, the semantic segmentation and pedestrian detection problems. The first data set we use is the Canada, which is published at ICPR 2020. It contains about 13,000 synchronized radar and camera frames. They capture the frames in a controlled environment, and the devices were mounted on a stationary car. Targets are including cars, pedestrians, and cyclists. They provide semantic segmentation labels on the range Doppler and range angle plane. The next dataset we use is captured by our research group. This dataset is published at the ITSC 2020. We captured the frames by synchronized radar, camera, and LiDAR, which were mounted on a moving vehicle. Moreover, the frames were captured on public roads in a city center, which increased the difficulty of detection problem. The network backbone we used is FCN and UNet. All the details were following the competitor's settings to make sure that the results would not be affected by different implementations. In all the experiments, we stacked 5 consecutive radar cubes at the input tensor. In the first experiment, we compare our proposed approach to competitors on semantic segmentation task using Canada dataset. The first row of the FCN-AS is trained on all the label data, and the second row is only trained on 30% label data. Our model was trained only on 30% label data and 70% unlabeled data. As can be seen in Table 1, our proposed semi-supervised method has clearly improved the performance with unlabeled data, especially the recall rate, which might be able to say that our self-weighting mechanism do improve the overfitting problem. In the second experiment, we compare the performance of pedestrian detection problem using the dataset released by our research group. The competitors were using external LiDAR sensor as the supervisor to label the frames automatically. But our model was trained only on 1,300 manual labels frames and about 7,000 unlabeled frames. We did not use the LiDAR sensor to supervise the training. Similar trends could be found in Table 2. As we can see, our method achieved comparable results as the competitors, but without using any external sensors to generate the annotations. In the final parts, conclusions. To the best of our knowledge, we're among the first to present a novel semi-supervised deep learning method based on the spatial-temporal consistency to alleviate the lack of annotation problem in radar datasets, and not limiting to the use of particular network backbones. We provide a general solution to exploit the unlabeled radar data on both semantic segmentation and pedestrian detection problem. Our method handles radar data by exploring potential of unlabeled frames instead of leveraging external sensors. The improved results over the baseline methods on the public datasets verify the feasibility of our proposal. And this is the reference page. Thank you.